So, István Biro, I'm going to give you your introduction. István has a background in physics, computer science, and 5 years of postdoctoral experience in controlled automation. He's currently a project manager at Heliotis AG. Is that how I pronounce it? Yeah. That's a Swiss company which is pushing the boundaries of white light lithography. So let's give them another little shout.
Thank you very much for the introduction. Hello everyone, welcome. So today we are going to talk about white light interferometry, and we are going to take the approach of how to measure roughnesses with it, and we will mainly focus on an industrial aspect. So this is the short agenda. After a brief introduction, we'll go around to see what roughness is, how to measure it, and then how to validate the measurements. And how to link roughness parameters to actual functional properties, what you want to achieve in the factory actually. So Heliotis is a company in central Switzerland, and Heliotis specializes in very fast industrial white light interferometers, like the devices you can see here. And as a short intro, what can interferometry in general do for you? White light interferometry is basically a non-contact optical measurement method which achieves nanometer resolution. So it's on the graph, it's on the high precision end, but very typically it's a fairly slow measurement technique. The specialty of Heliotis is actually trying to push it upwards to have the same resolution with substantially higher speed, up to 100 times higher speed. So with these specs, it becomes interesting to see if it's capable to measure roughness or not. And spoiler alert, yes it is. Why are we interested in roughness so much? That's the reason. So roughness is a really old topic, but it never gets old. It's actually on the rise. And you can see that from the market research study, but we have the same experience at Heliotis. We get increasingly more and more requests about surface roughness measurements, especially for very fine surface roughness measurements. So what is surface roughness? Basically, it's a component of surface finish, and there are some other components as well, as waviness, shape, and so on. And then there is the whole range of defect detection. We are not going to talk about that today. Obviously, we can do that as well. But time limits us, so we will keep ourselves to roughness. And if you would like to categorize roughness very roughly, we will put it into bins. One is area roughness, and the other one is profile roughness. And they are described by those two isonorms displayed there, and both of them have really a ton of roughness parameters. So it's a fairly complex issue. Most people think of roughness as RA, well there's a lot more behind it as just RA. So profile roughness is mostly measured with tactile instruments. On the other hand, surface or area roughness is typically measured by non-contact 3D methods, for example, white light interferometry. And of course, if you have a surface, there is nothing preventing you from taking a profile from it. So basically, if you measure an area away, you can actually measure both roughnesses. So the natural question that arises: how do they compare? So for that, let's compare very quickly. In this case, our Heliotis white light interferometer with pretty much any tactile measurement probe. And one of the first obvious issues that come up is surface modification. Do they have any effect on the surface? Do they alter it? And I think if you think of tactile versus non-contact, you can predict what's coming. So in these two examples, a roughness specimen or a roughness sample was measured with a tactile probe, and after that was measured with the white light interferometer. And actually you can measure out pretty much where the tactile instrument went along. It's even more surprising if you consider if I now read the result from the tactile instrument, it corresponds pretty exactly to what the roughness standard says. However, that's very untrue. So now you start wondering what happens there to actually measure the correct roughness. And for some applications, this might not be an issue. However, if you have soft surfaces or surfaces which cannot, for optical reasons, for instance, have scratches or indentations or any issues on them, for example, watch industry, you may not be able to use a tactile instrument. Or it might be beneficial for you if you are using one until now to switch to non-contact methods. So on the other side of the coin, there is the cost. So obviously, tactile, few thousand, PLI, few 10,000. For that money, however, you get with PLI a full surface, in the case of heliotis in a second or less, so really, really quickly, a lot of information, compared to a tactile probe, where you get one profile in several seconds. You can see the speed difference. And Heliotis is achieving this with a smart sensor where we have a lot of our processing actually in the pixels themselves. It's a principle with optical lock-in. And after that, we have an FPGA on board that crunches the volume and gives you back the surface. So that's the reason why it is so fast. And additionally, we have an implementation where we introduce these roughness libraries, these roughness measurement libraries in professional vision software into those which don't have it yet. And the reason for that is that we want to be out there. So in a lab environment, it's perfectly fine to be slow. Nothing will happen. There are no consequences for it. In a production line, you must keep up with cycle times, and those are typically very strict. So that's where the fast nature of white light interferometry comes in. Another pretty obvious issue is surface characterization. So if you look at this surface, you cannot really measure this with a tactile probe because you will not really capture the essence of the surface. So this is where the extra dimension coming from aerial measurement comes in. You can identify this surface much more uniquely with S parameters than with R parameters, or with aerial measurement versus tactile measurement. Now, the obvious issue in the industry is the age of these technologies. As I said, roughness is really old. So people tend to use tactile probes a lot. That's pretty much the norm in the industry, and that's what everyone knows. White light interferometry, or most optical techniques, are actually quite new. And if you look at this study, you can see that indeed, even today, contact measurements dominate. And even if you use some sort of aerial measurement, typically, profile modes or at least multiple modes, mixed modes are used. It's quite rare that people exploit the full benefit of aerial measurements. So obviously, there should be a transition, and there is a transition in the industry. But the big question is, how do we ensure comparability? And how do we convince our customer that indeed, if you switch to aerial measurements, he will get the same consistent results as he did in tactile, and that he gets comparable results to what he got in tactile, so he doesn't have to change his entire evaluation time. One way to do so is through direct comparison. So you can have certain surfaces and you can measure them tactile and with an aerial instrument, and you can compare the results. And that's what we have done with the tactile instrument and this white light interferometer for a round and flat surface. And you can see that the results match really, really well. So we get very similar roughness values that with tactile. That's already been used. So now people are asking, so why is it not perfect? Why do we not get the same? And that's pretty obvious. It's the physical reality that you look at a material through the eyes of the transfer function of your device. And that's different for tactile and for area. So you should never expect a complete match. And you have to consider that this transfer function depends on many things, among others, material properties, manufacturing methods. So you might get different matches. Just look at that. On the left-hand side, the heliotis measurement is a bit above, while on the other side it's a bit below the tactile result. And that has to do also with the surface machining method. Another way to do the validation is to reference and calibration targets. Why would you do that? Well, for instance, you might not have both instruments at hand. And the other reason, which is even more common and very, very important, is in industry, you would like to check the measurement capability of your machine in regular intervals. And that you can do very well with such a probe. So I was looking especially for samples which expose both R and S parameters. Here is one example. It's a symmetric target which is highly isotropical, and it has both results exposed. That's what happens when you measure it with an IoT device. You open this point cloud, and you get a profile, and then you look at the roughness values, and indeed you see the S and R values are pretty much what you expect. That's a nice confirmation. Now to the issue. What happens with the other parameters? Because most often when you buy such an artifact, you get 2, 3, if you're lucky, maybe 4 parameters stated. The others are not. So it's really hard to verify the other roughness parameters. Additionally, what you would like to have is a range of artifacts that covers different manufacturing methods and covers the modification of targeted modification of very specific roughness parameters. So for example, you would like to have your SQ value changed systematically. And that's really hard to get. And it's really expensive as well. So here's another artifact. This is an optical artifact, and it is made in such a way to allow you to do very, very isoconform evaluation of your measurement instrument. So they deposit patterns which correspond exactly to what the ISO numbers recommend. And we have, of course, measured that one as well. And indeed, we get the right SA and SQ values. So we can say very confidently that the device will measure the roughness accurately. Now, you have to consider the measurability of such artifacts as well. For example, what happens if you now start changing lateral resolution? That happens at 2 times, 4, 8, 20, 50. You can see by eye how the data is resolved better and better. So now, to your surprise, you will see that roughness values are actually estimated correctly for all the optics. And how can that be? Well, one reason is that it's a very well-engineered artifact. It has laterally coarse structures which allow you to measure it with multiple optics. That's not necessarily the case for all such specimens. And the other reason is that white light interferometers can measure for every lateral resolution the height with the same nanometer accuracy. So these 2 benefits result in matched roughness results throughout a very wide range of implementations. The other thing that you have to consider is the signal that you get back. And now look at the 2x picture, because especially in low magnification, shiny, steep structures tend to give you a very, very high contrast. So you get spots that are really dark and spots that are really, really bright. And we can, of course, measure it because we inherently have a method where we can ensure very high dynamic range of the sensor. That might necessarily always be the case. That's one thing you have to consider when choosing such an artifact. So we have seen the limitations. We have seen the limitation of direct comparability because of transfer functions. We have seen the limitations of calibration targets in terms of exposing certain parameters only and not covering the range of your manufacturing processes, and being, of course, really expensive, especially if you want something traceable. So what can you do? And the answer to that is use the complexity to your benefit. So I've told you there are many, many roughness parameters. And historically, it just happens that people tend to pick out those 3 in the R world. The same for the S world. However, it's not so bad here. You can see a wider spread. But the more exotic parameters are often ignored. So let's use them. And let's try to, instead of validating instruments backwards or using artifacts, let's try to link the actual measurement to functional properties. And this is an example where the authors have studied basically the effect of roughness on certain stress parameters in years. And it turns out that there is a certain set of roughness parameters, which you can see down there, which correlates really nicely with stress. So now this allows you to measure the roughness in the machine and actually predict how the gear is going to behave. Another example is from Toyotis, where we know that certain watch manufacturers like to customize their watch glasses. And one way to customize it in order to achieve certain optical properties or certain adherence properties, if you want to deposit something on it, for example, is to laser treat it. And this is a surface before and after laser treatment. Please notice the scale. So it's really, really fine surface modification. We are talking about nanometer surface changes here. And yet by eye, you will be able to tell the difference between the two. The question is now, how do we tell the difference in production? How do we say if the surface is now having the right properties or not? Is the process successful or not? And again, we can extract the roughness values. And let's just have a look at the ratio of the roughness values. So the roughness values on the left divided by the roughness values of the right-hand sample. And you get that graph down there where the x-axis shows the index of the roughness value. So obviously I didn't put the names there because it would be too large, but one corresponds to a certain name and so on and so on. And you will find that certain roughness parameters don't change that much. However, others change a lot. So now this is just n equals 1 sample, and that's why we took the ratio. And you can see that, for example, the very much used SA value is not that different. However, certain values are. And now if you just focus on those, you can indeed verify how well the manufacturing of this part went. Now, of course, later in the industry, we will not have n equals 1. We will have a lot of measurements, and we will do a statistical evaluation showing with more powerful means which roughness measurements are relevant. This is a pragmatic way to go. Let me summarize. We have learned today that roughness measurements are very much recent, and roughness measurements are very required in the industry, especially when it goes down towards low micron to tens hundreds of nanometer scale roughness. We have learned that the new measurement techniques are really, really good at measuring these. The issue is obviously ensuring the traceability backwards and the confidence of the customer that they can actually use this. And we have seen a couple of methods for solving this issue. So instrument-to-instrument comparison, artifacts, or as a matter of fact, the pragmatic way, which in most cases actually turns out the best. So with this, I thank you for your attention, and I invite you to have a look at our demonstration downstairs. We have a demo exactly on how white light interferometer works when integrated with an industrial SPS, and how we can evaluate the roughness and feed back to the machine in real time. Thank you very much.
Question over here.
Thank you for the presentation. It's a perfect introduction for mine, which is the next. I have a question. You compared the tactile system to the optical system, but there are also several optical systems and technologies for measuring surface roughness. My question is, did you also compare other optical systems or technologies to your system, and what were the results of this?
Yeah. So I didn't compare them directly to others. However, I actually did indirectly. And let me explain that the artifacts that you buy are certified with actually other instruments. So for example, the symmetrics artifact has the R parameters with tactile probe and the S parameters with the confocal microscopy. So indirectly it's in there. On the other side, comparison between VLI and confocal is pretty much there in literature in very, very large numbers. So that was not really the purpose here that exists up there.
Okay, thank you.
Take one more. Thank you. The chairman has to defer to me.
Thank you. So very briefly, my experience of white light interferometry is that on steep surfaces you miss large chunks. Effectively, a lot of the machines interpolate the data. And I think some of the parameters are more affected by that than others. It biases some of the parameters. And I'm thinking by looking at all those roughness parameters, we don't know which ones they are, that you're using a better set of measurable parameters to, if you like, interpolate the values that you've missed. Is that a reasonable way of thinking about it?
If you're thinking about using multiple roughness values and having a correlation where the input is multiple S or multiple R values to one function, you're perfectly right, and we do that as well. But not for the reason of missing points. Heliotis devices all have super high dynamic range. So on those artifacts which I have seen, we don't really miss many points. There are a couple of outliers, but the surface is typically represented in full. Obviously, if you have now a 19 degrees gold, yes, then you would miss, but pretty much no artifact has that. They are careful of not giving you something like that because no other measurement device can measure that either.
Right, that's why I was thinking actually, so the higher magnification lenses also have higher NA.
Correct.
So also have steeper capabilities.
That's why I was showing you that graph where I measured that artifact with multiple magnifications. And we got 50 times indeed, and you're right, it's not just the letter resolution. The NA increases on order of magnitude. So indeed, we can see the words better, but it's not likely that 2x I'm missing a lot of data. There are a couple of outliers, but that's pretty much it.
Okay,
thank you.
Okay, everybody, I think to keep things moving, we better let Clemens then come forward. So thank you again, it's really good.